June 15th, 1943. 25,000 feet above the English Channel, Royal Air Force Flight Lieutenant James Morrison pressed his pencil against the navigation chart, watching in frustration as the graphite tip crumbled under the vibration of his Spitfire's Merlin engine. The frozen air at altitude had turned the wood casing brittle. The lead and core snapped with each attempt to mark his position. The third time in 20 minutes, Morrison found himself unable to record critical navigation data. Below him, the choppy waters of the occupied channel stretched toward France. Above him, German fighters prowled the stratosphere. And in his cockpit, the most advanced fighting machine of its era was being defeated by a writing instrument that hadn't fundamentally changed since the 16th century. That morning, Morrison had watched two of his squadron mates forced to abort their mission when pea fountains leaked at altitude, flooding their navigation charts with useless ink. The extreme cold, rapid pressure changes, and constant combat vibration of create flight conditions that rendered conventional writing instruments unreliable or completely useless. Pilots across the Allied air forces faced the same maddening problem. They could master aircraft capable of 400 miles per hour, navigate by dead reckoning across hundreds of miles of ocean, and engage enemy fighters in three-dimensional combat. But they couldn't reliably write down their observations. What Flight Lieutenant Morrison couldn't have known was that 500 miles away in Buenos Aires, Argentina, a Hungarian journalist named László Bíró was putting the finishing invention touches on it that would solve his problem and revolutionize writing forever. Thed Moore Ballpoint pen represents it embo than just another writing instrument. Died a complete reimagining of how ink could be controlled, delivered under, and preserve the most demanding conditions imaginable. The mathematics of fluid dynamics, materials science, and precision manufacturing were going to create a tool that would prove conver more reliable than fountain pens, more durable than pencils, and more practical than any writing instrument that had come before. The transformation begun in 1938 when László Bíró, working as a journalist for Budapest newspaper, Grushin's cause frustrated with the constant interrude by fountain pen failures. Traditional fountain pens relied on capillary action to draw liquid from an ink reservoir through internal A-feed system to a metal nib. The process worked adequately under conditions, but failed catastrophically when subjected to temperature changes, altitude variations, or physical stress. Bíró had spent countless hours cleaning ink-stained fingers, replacing damaged nibs, and rewriting articles ruined by unexpected ink floods. The breakthrough came during a visit to a printing plant where Bíró observed the thick, fast-drying ink used in newspaper. This production ink, formulated to transferly from metal roll cleaners to paper without smearing or bleeding, possessed qualities that fountain pen ink lacked. It dried almost instantly, didn't run when exposed to moisture, and maintained consistent color density. But it was far too thick to flow through conventional fountain pen mechanisms. The viscosity that for printing made it perfect made it impossible to use in traditional writing instruments. Working with his brother György, a chemist, László Bíró began experimenting with ways to apply thick printing ink in controlled amounts. Their early prototypes used various mechanical systems to regulate ink flow, but each approach created new problems. Rollers were too large for practical writing instruments. Brushes wore out quickly and provided inconsistent coverage. Spring-loaded mechanisms jammed when exposed to temperature changes. The solution came from an unexpected source. While watching children play marbles in a Budapest park, László noticed how the spheres picked up mud as they rolled, leaving perfect trails behind them. The ball-bearing principle could be applied to writing. The concept seemed deceptively simple. A tiny steel ball precisely fitted into the tip of an ink-filled tube would rotate as it moved across paper. The ball would pick up ink from the reservoir and transfer it to the writing surface through direct contact. Gravity and capillary action would maintain ink flow to the ball. The viscosity of the ink would prevent flooding while ensuring adequate coverage. In practice, the engineering challenges proved enormous. The ball had to be manufactured at tolerances measured in thousandths of an inch. Too loose and ink would flood around the edges. Too tight and the ball wouldn't rotate smoothly. The ink formulation required precise viscosity, drying characteristics, surface tension, and the housing needed to maintain consistent ink pressure. While preventing contam, Georgi Biro's chemical expertise proved crucial in developing an ink formula that balanced competing requirements. The ink needed to be thick enough to prevent flooding, but thin enough to flow smoothly. It had to dry quickly on paper but remained fluid in the pen. It required resistance to temperature changes while maintaining consistent writing characteristics. After months of experimentation, they created an oil-based ink that performed reliably across a wide range of conditions. The formulation included dyes for color, solvents for viscosity control, and additives to prevent bacterial growth and chemical degradation. The mechanical challenges proved equally complex. The ball bearing had to be manufactured from materials that wouldn't corrode when exposed to ink chemicals. The socket holding the ball required precision machining to ensure proper fit while allowing smooth rotation. The ink reservoir needed internal structures to maintain consistent pressure and prevent air bubbles that could disrupt flow. Early prototypes failed in spectacular ways. Balls fell out during use. Ink dried in the tip, rendering pens useless after a few hours. Temperature changes caused expansion that cracked housing or compression that prevented ink flow. By 1940, the Bíró brothers had developed functional prototypes that demonstrated the potential of ballpoint technology. Their pens wrote smoothly, didn't leak when subjected to temperature changes, and required no maintenance beyond occasional cleaning. The thick ink dried almost instantly, eliminating the smearing problems that plagued fountain pens. Most remarkably, the pens functioned reliably at various altitudes and orientations, including fed fountain pens. The upside-down writing that was impossible with gravity. German invasion of Hungary in 1940 forced the Bíró brothers to flee Europe, taking their ballpoint pen patents and prototypes with them. They settled in Argentina, where László continued his journalism career, while György focused on perfecting the ballpoint technology. The move to South America proved fortuitous. Argentina's neutral status during World War II allowed them to continue development work without wartime restrictions. More importantly, they encountered Henry George Martin, a British accountant living in Buenos Aires who recognized the commercial potential of their invention. Martin understood something the Bíró brothers hadn't fully grasped. Their ballpoint pens solved problems that were becoming critical as aviation expanded and modern warfare placed unprecedented demands on writing instruments. Pilots, navigators, and military personnel needed reliable writing tools that functioned under extreme conditions. Traditional fountain pens failed at altitude, leaked during rapid pressure changes, and froze in cold temperatures. Pencils broke, smeared, and became illegible when exposed to moisture. The ballpoint pen offered solutions to all these problems. In 1943, Martin arranged for demonstrations of Bíró ballpoint pens to British military procurement officers. The timing was perfect. The Royal Air Force was expanding rapidly, training thousands of pilots and aircrew who required reliable navigation and communication tools. Bomber Command was conducting round-the-clock operations over Europe, where accurate record-keeping could mean the difference between successful missions and catastrophic failures. Fighter Command needed pilots who could quickly and accurately record enemy positions, weather conditions, and tactical observations. The demonstration that would change everything took place at RAF Northolt on a crisp September morning in 1943. Wing Commander Jeffrey Pike, responsible for aircrew equipment procurement, watched skeptically as Martin demonstrated the ballpoint pen's capabilities. Pike had seen dozens of proposed improvements to aircrew equipment, most of which proved useless under combat conditions. But as Martin wrote smoothly at various angles, including completely upside down, Pike's skepticism transformed into intense interest. The real test came when Martin placed the ballpoint pen in a pressure chamber that simulated conditions at 30,000 feet. Traditional fountain pens exploded or leaked catastrophically under such conditions. The ballpoint continued writing normally. When exposed to temperature variations from -40 to +120 degrees Fahrenheit, the pen maintained consistent performance. Most impressively, it wrote clearly on damp paper, greasy surfaces, and even through thin layers of ice that would render other writing instruments useless. Within weeks, the British government had placed an order for 30,000 ballpoint pens, specifically for aircrew use. The pens would be designated as official Royal Air Force equipment, distributed to pilots, navigators, bombardiers, and ground crews across the expanding Air Force. But this was only the beginning of a revolution that would transform not just military operations, but the fundamental way humans recorded information. The production first run of Royal Air Force ballpoint pens rolled off assembly lines at the Miles Aircraft Factory in Reading during the October. 40 pen required 1943. Each 7 individual components manufactured to tolerances that exceeded those used in aircraft instruments balls. The steel, precisely 0.7 millimeters in diameter, were ground and polished to mirror finishes that eliminated microscopic irregularities capable of disrupting ink flow. The socket housings demanded machining accuracy measured in 10,000ths of an inch. A deviation of Morrison's could render the entire mechanism useless. The ink formulation represented a triumph of wartime chemistry. Georgi-based solution Bíro's oil combined 17 different compounds in exact proportions. Aniline dyes provided color permanence that resisted fading under ultraviolet exposure. Oleic acid controlled temperature ranges from E-viscosity across Arctic cold to tropical heat. Phenol derivatives prevented bacterial contamination that could cause the delicate ball mechanism to malfunction. Alcohol maintained ink, bends fluidity while copper salts inhibited corrosion of metal internal components. Production emerged challenges immediately. The British manufacturing designed for aircraft infrastructure, components, and munitions struggled to adapt to precision writing instrument assembly. Traditional pen manufacturers lacked experience with the ball-bearing mechanisms. Aircraft manufacturers possessed precision machining capabilities but no understanding of ink chemistry. The solution required unprecedented cooperation between industries that had never collaborated. Squadron leader Patricia Walsh became one of the first RAF personnel to receive the November new ballpoint pens during 1943. As a navigation instructor RAF at Cranwell, Walsh trained hundreds of aircrew in dead reckoning, IAEN, and radio beacon procedures. Shed Witness had countless training flights disrupted by writing instrument failures. Student navigators struggling with frozen pencil calculations made errors that could prove fatal in combat. Instructors carrying backup fountain pens watched helplessly as altitude changes caused catastrophic ink floods across navigation charts. Walsh's first flight with a mission ballpoint pen occurred during a training over the North Sea. Flying at 22,000 feet in a reliability row Anson, she experienced the revolutionary AVI that would define ballpoint technology. The pen wrote smoothly despite cabin temperatures hovering near freezing. Rapid altitude changes during practice navigation ink exercises caused no flow disruptions. Most remarkably, when condensation formed on her navigation charts, the ball Ballpoint continued writing clearly traditional pens would have skipped or smeared. The psychological impact proved as significant as the technical advantages. Air CD to Carrie Rue, who had learned multiple writing instruments, as backup systems discovered they could rely on a single ballpoint pen throughout entire missions. Navigation calculations that previously protection required careful of writing materials could only be performed CAS combat conditions. Pilots found themselves making detailed notes about enemy positions, weather phenomena, and tactical observations that they would never have attempted for ballpoint pens, exceeded production 1943, demand with unreliable fountain pens, by capacity by enormous margins. The initial order for 30,000 units had expanded for over 200,000 pens as word spread through RAF squadrons. Bomber Command alone requested 50,000 units after aircrew reported unprecedented reliability during raids over Germany. Transport Command demanded 20,000 pens for Navig supply aiders flying missions across the Himalayas to where extreme altitude and temperature variations rendered conventional writing instruments useless. The Americans took notice. Colonel James, the Stuart actor serving Hollywood as a bomber pilot with the 8th Air Force, encountered bald British point pens during joint operations in early 1944. Stuart's missions over occupied Europe had been plagued by navigation equipment failures, including the constant frustration of writing instruments that failed under combat conditions. After borrowing a ballpoint from an RAF navigator during a mission briefing, Stuart immediately recognized the revolutionary potential. Stuart's enthusiasm reached the Pentagon through unofficial channels. His combat reports, written with borrowed British ballpoint pens, demonstrated clarity and detail that impressed intelligence analysts accustomed to fragmentary notes produced with unreliable writing instruments. Within weeks, American military procurement officers were demanding to ball access point technology for you. The technology S forces transfer proved complex. British authorities, recognizing the strategic value of reliable writing instruments, initially restricted ballpoint pen exports. The devices had become classified military equipment, subject to the same security controls governing radar components and encryption devices. American manufacturers attempting to reverse ball engineer capture point pens discovered the precision requirements and chemical formulations that production extraordin made materially challenging. Negotiations between British and American procurement intense agencies springified through 1944. The approaching Normandy invasion demanded unprecedented coordination between Allied forces, including reliable communication and record-keeping systems. Operation Overlord would involve 150,000 personnel in the initial assault, each for requiring Dable equipment dependent on the under-navigation, communication, and documentation most demanding combat conditions imaginable. The breakthrough came when Henry, still Martin managing ballpoint production in Argentina, proposed licensing agreements that would allow American manufacturers to produce pens using Biro patents. The arrangement required technology transfer that included not just mechanical specifications, complete chemical formulations, but the manufacturing processes developed through years of experimentation. American companies would pay royalties while gaining access to revolutionary substantial technology that could transform military operations. The first American-manufactured ballpoint pens emerged from the Eversharp Company's facilities in Chicago during May 1944. Its Eversharp had built reputation manufacturing mechanical pencils and fountain pens, but company executives recognized that ballpoint technology represented the future of writing instruments. Their production Linsley Rhett, Hastuled for ballpoint assembly, initially produced 300 pens daily, while engineers worked to increase output to meet military demand. Quality control proved the greatest challenge in American production. The precision ball bearings required specialized machinery that didn't exist in conventional pen manufacturing facilities. Each ball had to be inspected under microscopes to identify surface imperfections invisible to the naked eye. The socket housings demanded machining tolerances that exceeded those used in precision watch manufacturing. Even minor variations in component specifications resulted in pens that leaked, skipped, or failed completely after brief use. The D-Day landings provided the ultimate test of ballpoint reliability. American paratroopers dropping behind Omaha Beach carried ballpoint pens that functioned flawlessly despite extreme physical stress, temperature variations, and exposure to saltwater spray. British commandos assaulting Gold Beach used ballpoints to record German defensive positions while under direct fire. Naval officers coordinating the massive invasion fleet maintained detailed logs with writing instruments that performed reliably despite of the chaos hideous warfare. Lieutenant Colonel Robert Cole, leading 101 Thest Airborne's assault on Carentan, later testified to the revolutionary impact of reliable writing instruments. His after-action reports, written with ballpoint brief pens during lulls in fighting, provided intelligence analysts with unprecedented detail about German tactics, equipment, and defensive preparations. Previous had produce operations fragmentary notes, written with whatever writing materials survived combat conditions. The ballpoint enabled comprehensive documentation that proved invaluable for planning subsequent operations. Themes during D-Day operations, success of ballpoint P Allied military hierarchies that no created a ripple effect throughout procurement officer had anticipated. By August 1944, field commanders across the European theater were requisitions for ballpoint pens, with submitting urgent reserved for ammunition, a desperation typically in medical supplies. Major General Maxwell Taylor, commanding the 101st Airborne Division, issued a direct order that every officer above the rank of lieutenant must carry a ballpoint pen during combat operations. His reasoning was brutally practical. Traditional writing instruments had caused more mission failures than enemy action in several recent operations. The phenomenon extended beyond individual reliability and detail. Intelligence analysts at combat units equipped with ballpoint pens began producing after-action reports of unprecedented quality. Supreme Headquarters Allied Expeditionary Force noticed that units using ballpoints generated 3 times more actionable intelligence than those relying on conventional writing instruments. The difference wasn't just quantity, but precision proved accurate to within 50. Coordinates recorded with ballpoints meters. Weather observations written during combat provided meteorologists with data quality that rivaled peacetime scientific stations. General Omar Bradley, commanding the First Army during the breakout from Normandy, recognized that reliable documentation had become a force multiplier. His staff officers, equipped with ballpoint pens, maintained by dozens of miles. Tank commanders could operational logs that enabled real-time coordination between units, separated record enemy positions while under fire. Artillery observers could calculate firing solutions without war snapping. Radio rhying about ink freezing or pencil leads and messages accurately despite cramped conditions, and constant operators could transcribe coded as significant as the tactical advantages. Officers' vibration. The psychological transformation proved who had learned to limit brief sketches to detailed operational orders documenting everything. Battle plans expanded from liability suddenly found themselves written communications due to instrument unary fragmentary notes to comprehensive intelligence. Reconnaissance reports evolved from assessments. Supply requisitions became precise inventories rather than desperate approximations. The ballpoint pen had eliminated a constraint that military personnel hadn't even recognized was limiting their effectiveness. German intelligence officers analyzing captured American equipment in late 1944 initially dismissed the ballpoint PTIEs. The Wehrmacht advanced optical equipmentins as curious novel, developed sophisticated encryption devices and precision instruments for artillery calculation. Yetzi during winter operations on the Eastern Front. For centuries, German officers carried their forces continued struggling with the same writing instrument limitations, fountain pens that had plagued armies. Luftwaffe pilots and failures at altitude that dured pencil, American and British aircrew had eliminated. The ballpoint pen that emerged from a Hungarian journalist's frustration with ink-stained fingers became the unsung hero of Allied victory. From Flight Lieutenant Morrison's frozen cockpit above the English Channel to the beaches of Normandy, László Bíró's revolutionary design solved problems that had plagued military operations for centuries. The simple steel ball that rolled across paper carried more than ink. It carried the reliability that transformed fragmentary combat notes into comprehensive intelligence, turned desperate supply requests into precise logistics, and enabled the detailed documentation that won wars. Today, billions of ballpoint pens flow across paper worldwide, each one descendant of that first prototype tested in Argentine laboratories. The next time you click a ball, point pen, remember that you're holding a weapon of war disguised as an everyday writing instrument.